So in this video we're going to look at another inequality with our geometric sequences using the nth term, and this time we're going to use a slightly different logarithm rule, but as I said in the last video, you can use either method. In fact, there are more methods because really you can use logs to any bases with these as long as you're careful with them. But this is another one which can be quite nice to use. So for this problem, we're given a geometric progression as a first term of 30 and a common ratio of 1.1. Which term is the first to be above 1000? So we're going to set this up and let's extract our key information. So our A value, our first term, is 30. R is our common ratio R, which is 1.1. Well, we're looking at which terms. We're looking at using the nth term formula, and it's a geometric, so we can substitute in and say that we have 30 multiplied by our R value, which is 1.1 to the power of n minus 1. And we are looking for when this term is above, so in other words, greater than 1000. So let's move this 30 then and say that we've got 1.1 to the power of n minus 1 is greater than 1000 over 30, which simplifies to 100 over 3. Let's leave it as a fraction. Now, at this point, we're going to need to take logarithms of both sides, and you can use natural logarithms like in the last video, or you could use log to base 10, or you can use logs to any bases as long as you take it at both sides. But quite a nice one is going to use the fact that we have a 1.1 as an exponential there and take a log to base 1.1. So log to base 1.1 of 1.1 to the power of n minus 1 is greater than log to base 1.1 of 100 over 3. And your calculator is a specific button so that you can put any base in there. Well, it's a similar idea as with the last video, so we can move the power to the front as a multiplier. So n minus 1 times log to base 1.1 of 1.1 is greater than log to base 1.1 of 100 over 3. And you might be wondering as well, do we need to be careful of the sign? And you do, but because our log is base 1.1, so it is a positive, it's a base which is greater than 1 there, it means it's going to generate a positive value. If the log was, say, log to base 0.5, that will generate a negative number, so then you do have to be careful with the sign changes. So you would have to switch the inequality there. So it is something to also be careful of. Now, the reason this one is quite a good technique is log to base 1.1 of 1.1 just simplifies to 1. Okay, so they cancel, leaving you with 1. So in other words, we have n minus 1 is greater than log to base 1.1 of 100 over 3. And therefore n is greater than log to base 1.1 of 100 over 3 plus 1. And that would be an exact point with our inequality. Well, we don't want it like that because that's not that helpful to us. So let's convert it to a decimal. So we can say n is greater than 37.791. Well, we know our n value because it represents terms in the sequence. Must be an integer value, so we can say for this inequality that n is equal to 38, or in other words, we're looking for the 38th term. Well, because we actually want to know which term it is, now that we know it's the 38th term, we just need to use that along with the first term and the common ratio and substitute it into the nth term formula. So we have n equals 38, a is equal to 30, r is equal to 1.1. If we substitute it into the nth term formula, we have 30 times 1.1 to the power of n minus 1, So 38 minus 1, which is 37, which is approximately equal to 1020.118,458. Okay, so 1020.118,458. And like the last one, we can do a bit of a check at the end. Because we're looking at n is greater than 37.791, which is why we use 38. If you try 37 and do 37 minus 1 for your power there, which would be 36, you'll find that that is just below 1,000. So that's a little bit of check at the end just to make sure that you're correct. But that would be the first term greater than 1,000 for this geometric progression.